Hello students, welcome to EPG Pathshala. I am Dr. Vishwanath Tiwari from Central University of Rajasthan. Today I am going to discuss about a module that is known as Enzyme Kinetic Parameter. This has been taken from the paper Molecular Enzymology and Protein Engineering. As you know that enzymes are the biocatalyst which has efficiency, a specificity and have mode of regulation. And the parameters which are used to explain the kinetics of the enzyme are known as enzyme kinetic parameters. And as you know that enzyme kinetic parameter consists of Michaelis-Menten constant, maximum velocity, turnover number and a specificity constant. So in this module we will discuss about Michaelis-Menten constant. We will also discuss how this Michaelis-Menten constant is associated with the binding affinity of the substrate with the enzyme. At the same time, we will also discuss about how the Km of the enzyme is responsible for the regulation of the metabolic pathways. We will also discuss about how maximum velocity is responsible for the product formation. We will also discuss how the turnover number is responsible for selecting a particular substrate. And in we will also discuss about the questions related to the different kinetic parameters. Before going into the details of enzyme kinetic parameter, I would like to give you brief introduction how your product formation takes place from the substrate. So enzyme combined with the substrate with the rate constant of K plus 1, and that will lead to the production of ES complex. Then ES complex is converted into the product with the rate constant of K plus 2. We have another rate constant that is known as K minus 1 that is responsible for breaking ES complex not into the formation of product but formation of the substrate plus free enzyme. So K minus 1 is a rate constant that is responsible for the breakdown of ES complex into the free enzyme and substrate. So if you see this equation, then you can say that the product formation takes place when we have the production of ES complex, and ES complex will lead to the formation of the product. That means K plus 2 must be greater than K minus 1. If you know that velocity of a reaction is dependent on the product formation. So velocity is the product form per unit time. So basically it is a product concentration that is giving you information about the velocity of the reaction. The first kinetic parameter is Michaelis-Menten constant, that is denoted by Km. Michaelis-Menten constant or Km gives idea about how much substrate concentration is required to achieve a fraction of Vmax or ES complex. Michaelis-Menten equation is written as V0 is equal to Vmax into S upon Km plus S, where V0 is the initial velocity, Vmax is a maximum velocity, and S is substrate concentration, and Km is a Michaelis-Menten constant. The fraction of velocity achieved is explained by V0, that is initial velocity, divided by Vmax, that is a maximum velocity. So based on Michaelis-Menten equation, the fraction of velocity achieved can be calculated by V0 upon Vmax is equal to substrate concentration divided by Km plus S. If value of V0 is equals to half Vmax, that means initial velocity reached to the half Vmax, then the relation between Km, that is Michaelis-Menten constant, and substrate concentration can be calculated. When you putting the value of V0 as half Vmax, then the equation of Michaelis-Menten equation is rearranged in such a way that you can see that one half of the Vmax is achieved. So Vmax and Vmax get cancelled. So one half is equal to substrate concentration divided by Km plus substrate concentration. If you rearrange this equation, then you can have another relation where Km is equals to substrate concentration. So in this way you can say that if initial velocity is half of the Vmax, then Km is equals to substrate concentration. Another word, you can also say that Km is nothing, is basically a substrate concentration that is required to achieve half of the Vmax. So if you see in the graph, with the substrate saturation, the reaction rate increases and a condition is reached where further increase in the substrate concentration does not increase the maximum velocity. So if the half Vmax is calculated on the graph and its corresponding substrate concentration that is seen on the x-axis is going to be your Km. So Km is having unit which is same as the substrate. So it concludes that Km is equals to the substrate concentration that is required to achieve half of the Vmax. Similarly, other relation can be calculated in the similar way where we are not considering V0 as half Vmax. So we are taking other case where V0 is equals to 1/3 of the Vmax. Then what is the relation between Km and substrate concentration? So to calculating this, we are putting V0 as equal to 1/3 Vmax into the Michaelis-Menten equation. And if you solve that equation, then you will see that the relation come out is Km equals to doubles of the substrate concentration. So if you're putting this particular condition, then you have another definition here. That is, Km is doubles of the substrate concentration that is required to achieve 1/3 of the Vmax. Similarly, other calculation can be done where we are putting V0 is equal to 1/4 of the Vmax. Then the relation between Km and substrate concentration will be Km is equals to triples of the substrate concentration. So in this case, you can say that Km is triples the substrate concentration. Km is equals to triples of the substrate concentration, which is required to achieve 1/4 of the Vmax. Another relation between Km and substrate concentration can be calculated. For example, if you're taking V0 as equals to 3/4 of the Vmax or 75% of the Vmax achieved, then the relation will be Km is equals to 1/3 of the substrate concentration. And we can say that Km is 1/3 of the substrate concentration which is required to achieve 3/4 of the Vmax. So in this way, another problem can be asked where the fraction of velocity is not given, but fraction of Vmax achieved in term of percentage is given. For example, if V0 is half Vmax, then 50% of the Vmax is achieved. When V0 is equal to 3/4 of the Vmax, then 75% Vmax is achieved. So if you're saying that 50% Vmax is achieved, then Km is equal to substrate concentration. Similarly, if V0 is reached to the 90% of the Vmax, then the relation between Km and substrate concentration will be Km is equals to 1/9 of the substrate concentration. Based on the above discussion, there is a number of relation that can be calculated between Km and substrate concentration. Then question arises, which value of the Km is taken as a Km of enzyme? So the relation which are frequently used to explain Km or Michaelis-Menten constant of the enzyme is substrate concentration at which reaction rate is half maximum, and this particular value is used as a reference. So whenever you are saying enzyme have the Km of, let's say, X, so that particular X is the substrate concentration that is required to achieve 1/2 of the Vmax. So in this table you can see that there are different enzymes, they are having different Km. For example, carbonic anhydrase, that is responsible for synthesis of bicarbonate, is having Km of 26 into 10 to the power minus 2 molar. Catalase enzyme, that is involved in the detoxification of H2O2, having Km of 1.1 molar. Beta lactamases, they are the enzyme that is involved in the hydrolysis of penicillin group of antibiotics or beta lactam of antibiotics. They have Km of 2 into 10 to the power minus 5. Hexokinases have the Km of 5 into 10 to the power minus 5 for glucose, and chymotrypsin has the Km of 2.5 into 10 to the power minus 5. So every enzyme is going to have different Km for its own substrate. Not only that, if one enzyme having multiple substrate, they have different Km for different substrates. The relation between Km and binding affinity, because we are talking about substrate concentration that is required to achieve a fraction of Vmax. Substrate is bind to the active site of the enzyme, so the binding affinity between active site of the enzyme and substrate is very important. So Km also explain about the binding of substrate and enzyme, and also explaining the formation of ES complex. And Km is explaining the formation of ES complex based on the interaction between substrate and enzyme. So Km is inversely related to the binding affinity of the substrate to the enzyme. That means if an enzyme is having less Km, will have better binding affinity by the substrate. You can understand it in this way, that if Km is low, you require low concentration of the substrate to achieve half Vmax. It is only possible when affinity between substrate and enzyme is very good. So based on the relation between Km and binding affinity, we can solve one question here. Consider an example where we have three enzymes V1, V2 and V3 which have Km of 3 millimolar, 4 millimolar and 1 millimolar. Then following observation can be drawn from these experimental results. If you compare V1, V2 and V3 and their respective Km, then you can say that enzyme V3 have better interaction with the substrate because they have lowest Km. I already told you that Km is inversely related to the binding affinity. So if Km is lower, then enzyme have better affinity. Similarly, order of interaction from highest to lowest can also be calculated, and which is going to be the V3 have highest binding affinity, followed by the B1, and in the last V2 which is having lowest binding affinity. And if you see the Km, they are arranged with increasing the Km, where V3 have the lowest Km and V2 have the highest Km. Km can also be related to the regulation of metabolic pathways. If you remember any metabolic pathway, for example, let's say glycolysis, we always have n number of metabolic pathway, and conversion of a substrate into the product is always mainly dependent on the slowest step. So if you know the slowest step of an enzyme pathway or a metabolic pathway, then you can design that slowest step in such a way that, or you will modify the enzyme involved in the slowest step in such a way that you can enhance the metabolic activity. So it is also important to know about the regulation of metabolic pathway and Km. So the Km is low, then it has a more affinity. If Km is high, then the affinity is less. And the regulatory step is always slowest step. Then enzyme which is going to have highest KM is going to be the slowest enzyme. Therefore, if you have a metabolic pathway and you have different enzyme, the enzyme which is having the highest KM for its own substrate is going to be the slowest enzyme or regulatory enzyme or rate determining enzyme of a metabolic pathway. So we will discuss how Km is related to the metabolic pathway. So we have a question here. A is converted into B with the help of enzyme EA, B is converted into C with the help of enzyme EB, and C is converted into D and D is converted into E. And the Km of different enzyme EA, EB, EC and ED are 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 5 and 10 to the power minus 4 respectively. If all the substrate and products are present at the concentration of 10 to the power minus 4 molar, then which enzyme is going to be the rate limiting enzyme for the conversion of A into E? Student, as you know that a metabolic pathway which is slowest is going to decide the fate of a particular pathway, and you also know that Km is inversely related to the binding affinity of the substrate. So if an enzyme is going to have highest Km, it is going to have least affinity for a particular substrate. So in the given 4 enzymes, it is the EA that is going to have highest Km, which shows that it is going to have the least affinity for the substrate. Therefore, the rate limiting enzyme is going to be the EA, which is going to have highest Km. After discussion of Michaelis-Menten constant, the next kinetic parameter will be the maximum velocity, that is denoted by Vmax. So Vmax is defined as a maximum velocity achieved by the enzyme when it is fully saturated with the substrate. It is important to note here that enzyme must be fully saturated with the substrate if you want to achieve the Vmax. The Vmax cannot be achieved when you have suboptimal concentration of substrate. So the Vmax, if you remember the kinetics of enzyme substrate reaction, then Vmax is dependent on two things. First thing is, what is the concentration of ES complex? The second point is, what is the value of K plus 2? Therefore, the Vmax is equivalent to the K plus 2 into ES concentration. It is very important to note here is that it is very difficult to determine the concentration of ES complex, because concentration of ES complex can be calculated if you know the total enzyme concentration and you know the free enzyme concentration that is remain in a particular solution. So it is very difficult to determine what is a free enzyme concentration when a reaction is going on. But if you considering the assumption of steady state where substrate concentration is very much greater than enzyme concentration, then any point of the time during the reaction, the ES complex which is formed is always dependent on enzyme concentration. In the steady state, the free enzyme concentration is 0. Then ES complex is equals to total enzyme present, because in the steady state we never have any free enzyme. Therefore, the velocity equation is modified in such a way that where Vmax is equals to K plus 2 into total enzyme concentration. Therefore, we can conclude that Vmax is dependent on enzyme concentration and K plus 2. We have a question here which is asking how we are going to calculate the Vmax of a reaction. So we have enzyme activity that is defined as the amount of enzyme that hydrolyzes 10 micromole of pyrophosphate in 15 minutes at 37 degrees centigrade under standard assay condition. So this is an information given for that enzyme. So the purified enzyme have the Vmax of 2800 unit per milligram of the reaction enzyme. How many moles of the substrate are hydrolyzed per second per milligram of enzyme when substrate concentration is very much greater than the Km? 2-3 points are very important in this question. The first one is you're putting substrate concentration which is higher than the Km. That means you're putting abundance of the substrate. At the same time, they are giving you the Vmax, but they are giving you Vmax in the unit. So they are giving you Vmax is equal to 2800 unit per mg of the enzyme. But they are also giving one thing, that 1 unit of the enzyme is the one that hydrolyzes 10 micromole of the pyrophosphate in 15 minutes. So therefore you can calculate what is a Vmax in terms of substrate hydrolyzed per second. So Vmax is going to be 2800 units. So if you're putting 1 unit as a 10 micromole pyrophosphate, so 2800 multiplied by 10, so it is going to be 28,000 micromoles of the pyrophosphate converted per 15 minutes. But they are asking you how many moles of substrate are hydrolyzed per second, and you know that in 1 minute we have 60 seconds, so that can be calculated in terms of second. So the Vmax is going to be 28,000 divided by 15 into 60. So 28,000 divided by 900 seconds, and answer is going to be 31.1 micromoles. After discussing with the two kinetic parameters, the Km and Vmax, we will now discuss the third kinetic parameter, and that is known as turnover number or catalytic constant, and it is represented by kcat. So by the definition, turnover number is defined as maximum substrate converted into the product per unit time by unit enzyme in a given time when enzyme is fully saturated with the substrate. If you see the definition, 3 points are very important. First thing, you are putting enzyme as a unit. So enzyme concentration is constant. You are fixing a particular time, that means time is also constant. At the same time, you're putting abundance of substrate, so substrate is not limiting. So if you're putting these three conditions, what is the maximum number of substrate converting into the product is the turnover number. If you remember, the velocity of a reaction that is dependent on ES concentration, and conversion of ES complex into the product is dependent on K plus 2. So basically K plus 2 is nothing, is a kcat, which explain you about what is the rate of product formation, and it is expressed in the universe time, like second inverse minute, and this is a first order rate constant. In the table you can see that what are the kcats of different enzyme. For example, carbonic anhydrase, this is one of the highest kcat enzyme, is going to have kcat of 4 into 10 k power 7. Catalase enzyme have kcat of 40,000. Beta lactamases have kcat of 2000. Hexokinases have kcat of 218, and chymotrypsin have kcat of 0.24. If you see all the kcat, then you can say that chymotrypsin is very slow in converting ES complex into the product. At the same time, carbonic anhydrase is very fast in the converting ES complex into the product. As we have discussed about turnover number, so let's discuss a question where we are going to calculate turnover number of an enzyme. So we have a carbonic anhydrase with a concentration of 10 k power minus 5 molar, which converts bicarbonate into its product. And the concentration of the bicarbonate which is converted by this enzyme is 0.6 molar per second. So what is the turnover number of this enzyme? As you know that the concentration of the substrate converted into the product is going to the Vmax. So here in this question 0.6 molar of the substrate is converted into the product, which shows that it is going to be the Vmax of this enzyme, and Kcat is equals to Vmax by Et, and the Vmax of this enzyme is 0.6 molar and the Et is 10 to the power minus 6 molar. So if you solve this question, you will find the answer is 6 into 10 to the power 5 second minus 1. The question may ask that where the concentration of enzyme is not given and they are giving you the weight of the enzyme, and they are also giving you molecular weight of the enzyme. So if molecular weight of enzyme is given, weight of the enzyme is given, then concentration of enzyme can be calculated by using the molarity formula. Similarly, we can also calculate the concentration of the substrate that is converted to the product per unit time. We have an example where sugar polymer is hydrolyzed into the monomer by an enzyme, and the concentration of the enzyme is not known here. But we know that enzyme is present in terms of weights like 20 microgram and its molecular weight is 2 lakhs. The rate of monomer sugar, where we also don't know what is a concentration of sugar, but we know the molecular weight. So the rate of monomer sugar was determined to have maximum velocity of 10 mg per second. That means sugars converted into the product is having velocity of 10 mg per second and the concentration of enzyme is 20 microgram. So two important points if you want to solve this question. The first important point is the concentration of enzyme and concentration of the sugar or concentration of the product or substrate are different, because one is written in microgram, other is written in the milligram. So first thing, if you want to solve this question, you have to make both equals. So we are converting here the maximum velocity, that is 10 mg, into 10 into 10 to the power 3 microgram per second. The second point is they are not giving you the concentration. So how you are going to calculate the concentration? But they are giving you the weight as well as molecular weight, and you know that the molarity is equals to the moles of the solute in per liter of the solution. So moles of the solute can be calculated by dividing the weight which is given here divided by its molecular weight. For example, in the case of enzyme, the molarity will be 20 divided by 2 lakhs. One more interesting point here is that sometimes molecular weight is given in the Dalton. So Dalton is always the unit of molecular weight. So you don't have to worry about Dalton. So in this way you can calculate the concentration of enzyme, the concentration of sugar that is converted to its product or maximum velocity, and then turnover number can be calculated by dividing the Vmax with the Et. And if you solve the question, the answer is going to be 2.5 into 10 to the power 5. Up to this point, we have discussed about Kcat, Vmax and Km. If you know that when we are talking about Kcat, ES2 product formation is highlighted. When you're talking about Km, the formation of ES complex is highlighted. But when you're talking about the real catalysis, until we don't know both the kinetic parameter, we cannot say what a particular enzyme is efficient or not. For example, if an enzyme is having low Km, it will have better affinity. So more ES complex will form. But at the same time, if Kcat is low, then ES is not converted into the product. so we will have less efficiency. Similarly, if your Km is high, then we have less ES complexes formed, but if you have high kcat, all the ES complexes convert into the product. But until you don't have ES complex, you will not have the formation of the product. So it is very important when you're talking about the efficiency of the reaction, then you have to have another kinetic parameter, and that is kcat by km, which shows that if you want a reaction to be fast, then it must have high kcat. That means conversion of ES complex into the product is high. At the same time, it has a low Km, so the more ES complex is formed. So if the kcat by Km is higher, it is indicating higher kcat by Km is because of either high kcat, so more fast conversion, or low Km, so most ES formation. Therefore, we can say that to explain the overall efficiency of the enzyme, neither Km is important, neither kcat is important alone. But if you're taking both together, they are important, and that is represented by kcat by km. So you can say that kcat by km explains the efficiency of an enzymatic reaction. So efficiency constant, or kcat by km, is also sometimes referred as a specificity constant. So you have information of a specificity constant that is similar to the efficiency constant. So a specificity constant is defined as a rate constant for conversion of substrate to the product. And a specificity constant is dependent on total enzyme concentration and substrate concentration. Therefore, it is a second order rate constant and has a unit of mole inverse second inverse. In this table, you can see that different enzymes have different Km, different kcat, and different kcat by km. So km tell you about binding affinity of enzyme and substrate, kcat tell you about product formation, but kcat by km tell you about overall efficiency of the reaction. For example, if the affinity of catalase with the H2O2 is considered, then out of these 5 enzymes, it is the catalase enzyme which is having 1.1 km, carbonic anhydrase have 26 into 10 to the power minus 2 km, and if you see all the km, you will find that it is a beta lactamases which is going to have 2 into 10 to the power minus 5 km, and which is the lowest among all the 5 we have. So therefore, beta lactamase have high affinity for its substrate, that is benzyl penicillin. At the same time, catalases is going to have least affinity for the substrate. Similarly, if you see the kcat, you can say that catalase enzyme have fastest conversion of ES into the product, while chymotrypsin have slowest conversion. But overall efficiency of reaction is not going to decide by anyone alone. For example, if you see that beta lactamases have highest affinity for substrate, but they also have kcat by km highest, so they are more efficient. Even they are more efficient as compared to the catalase, which is having highest kcat by km. So therefore, we can say that it is a kcat by km that decides efficiency. But when you're talking about the maximum efficient enzyme, and if you see all the constant, you will know that any enzyme doesn't have higher rate constant to the k plus 1, because it is the constant which is responsible for the ES formation. So if for a very efficient enzyme, kcat by km must be equals to k plus 1. So if you know the km is equals to k plus 2 plus k minus 1 divided by k plus 1. So the km is having another form where k plus 2 can be replaced by the kcat. But for very fast reaction, you know that K plus 2 is very much greater than the K minus 1. Therefore, as compared to the K cat or K plus 2, K minus 1 is negligible. Therefore, the K plus 1 is equals to K cat by Km. That's what I'm trying to say is, if you have a fast enzyme, K cat by Km is equals to K plus 1. So we have discussed about K cat by Km. So let's solve a question that is based on K cat by Km. So we have an enzyme that is amino peptidase that converts tripeptide into its product. So we will have 4 tripeptides that is converted into the product, and we have calculated the different kinetic parameter for these 4 substrate. The first substrate is L-proline, glycine and glycine, which has kcat 384.8 and Km 1.3 millimole. So kcat by Km is calculated by dividing the kcat by Km. So the value is going to be 290. Similarly, if the kcat by Km is calculated for the second substrate, L-leucine, glycine, glycine, it is going to be the 380. Similarly, kcat by Km is calculated for the third substrate and it is going to be the 243. The third substrate is L-alanine, glycine and glycine. The fourth substrate is L-alanine, alanine, alanine. And kcat by Km for this substrate is 596. So based on these values, we may have different questions. First question is, which substrate is hydrolyzed most rapidly? So when we are talking about the substrate hydrolysis, so you have to see that which substrate is having highest kcat by Km, because if they are having highest kcat by Km, then they have most efficiency. Therefore, you can see that in all the 4 substrate, it is a fourth substrate, that is L-alanine, alanine, alanine, has the highest kcat by Km. Therefore, it is going to be the answer of this question. The second question can come based on this experimental data, which is the slowest hydrolyzed substrate. The slowest hydrolyzing substrate is going to have the least kcat by Km, and based on the experimental data, it is L-proline, glycine and glycine is going to be the slowest hydrolyzing substrate. The more question can be formed based on this data, such as which substrate have highest binding affinity. So the binding affinity is decided only by the Km. So if any enzyme having highest Km, then it is going to be the slowest binding affinity. If an enzyme is having lowest Km, then it is going to be the highest affinity for the substrate. So based on this experimental data, by looking the Km only, we can say that it is the L-leucine, glycine and glycine which is going to be the highest binding affinity for a particular enzyme. So we have discussed about kcat by Km. So let's solve a question that is based on kcat by Km. So we have an enzyme that is amino peptidase that converts tripeptide into its product. So we will have 4 tripeptides that is converted into the product, and we have calculated the different kinetic parameter for these 4 substrate. The first substrate is L-proline, glycine and glycine, which has kcat 384.8 and Km 1.3 millimole. So kcat by Km is calculated by dividing the kcat by Km. So the value is going to be 290. Similarly, if the kcat by km is calculated for the second substrate, L-leucine, glycine, it is going to be the 380. Similarly, kcat by km is calculated for the third substrate and it is going to be the 243. The third substrate is L-alanine, glycine. The fourth substrate is L-alanine, alanine, and kcat by km for this substrate is 596. So based on these values, we may have different questions. First question is, which substrate is hydrolyzed most rapidly? So when we are talking about the substrate hydrolysis, so you have to see that which substrate is having highest kcat by km, because if they are having highest kcat by km, then they have most efficiency. Therefore, you can see that in all the four substrate, it is a fourth substrate, that is L-alanine has the highest kcat by km. Therefore, it is going to be the answer of this question. The second question can come based on this experimental data, which is the slowest hydrolyzed substrate. The slowest hydrolyzing substrate is going to have the least kcat by km, and based on the experimental data, it is L-proline, glycine is going to be the slowest hydrolyzing substrate. The more question can be formed based on this data, such as which substrate have highest binding affinity. So the binding affinity is decided only by the Km. So if any enzyme having highest Km, then it is going to be the slowest binding affinity. If an enzyme is having lowest Km, then it is going to be the highest affinity for the substrate. So based on this experimental data, by looking the Km only, we can say that it is the L-leucine, glycine, which is going to be the highest binding affinity for a particular enzyme. Based on this experimental data, which is the slowest hydrolyzed substrate. The slowest hydrolyzing substrate is going to have the least kcat by km, and based on the experimental data, it is L-proline, glycine is going to be the slowest hydrolyzing substrate. The more question can be formed based on this data, such as which substrate have highest binding affinity. So the binding affinity is decided only by the Km. So if any enzyme having highest Km, then it is going to be the slowest binding affinity. If an enzyme is having lowest Km, then it is going to be the highest affinity for the substrate. So based on this experimental data, by looking the Km only, we can say that it is the L-leucine, glycine, which is going to be the highest binding affinity for a particular enzyme. So based on all the discussion, now we can have all information about different kinetic parameters. For example, in this exercise, you can see that Km gives you information about binding affinity of the substrate with enzyme. Vmax give information about maximum velocity of the reaction. Kcat give information about rate of product appearance, and kcat by km give information about overall efficiency of the reaction. So if you know these four kinetic parameters, that will help you to understand the process of enzyme kinetics. So students, let's now summarize what we have learned from this module. So in this module, we have discussed about four kinetic parameters. The first one is Michaelis-Menten constant. the second one is Vmax, the third one is turnover number, and fourth one is efficiency constant. The Maclaurin constant explains about the binding affinity of substrate with the enzyme, and we have learned that the enzyme affinity is inversely related to the Km of the enzyme for a particular substrate. At the same time, we have also discussed how the Km is used to explain the regulatory step of a particular pathway. The second, we have discussed about the Vmax, where we have discussed what is the velocity of appearance of the product. And third kinetic parameter, we have discussed about the turnover number, which explains again about the product formation, but the rate of product formation. Fourth kinetic parameter is kcat by km, which we have discussed. As you know that about km and kcat. Kcat explains what is the rate of appearance of the product. Km explain what is the binding affinity of enzyme with the substrate. But if you are considering only one kinetic parameter, either they explain how your substrate bind to the enzyme, or they are explaining how the ES complex is converted into the product, but they are not saying about the efficiency of the enzyme. So if you are talking about efficiency of the enzyme, you have to consider both these kinetic parameters, where the Km explain up to the ES formation and Kcat explain conversion of ES into the product. And the Kcat by Km is a constant, where if the rate of product formation is fast, then Kcat by Km is high. If the affinity of your enzyme with the substrate is high, then Km is low. That will also leads to the high Kcat by Km, because Km is present in the denominator. So in this way, you can say that overall enzyme catalysis is mainly decided by the efficiency of a particular enzyme, and the regulatory steps is also decided by the Kcat by Km. So in my view, as well as based on the discussion, it is a Kcat by Km that is going to play a very significant role when we are talking about enzyme kinetics as well as efficiency of a particular enzyme for production of a particular product. Thank you very much.